In the present video, we will discuss the GATE previous questions on basic concepts of thermodynamics and Zeroth law. Let's see the first question. Which one of the following is an intensive property of a thermodynamic system? Option A, mass. Option B, density. Option C, energy. Option D, volume. We know that intensive properties are independent of size or mass in the system. So mass is a direct measurement of amount of the matter. So it is a extensive property. And energy is which depends on the total amount of matter and the specific conditions. So energy also depends on the mass and it is also extensive property. And volume indicating the three-dimensional space occupied by the matter. So volume also depend on the mass and it is also extensive property. Both mass and volume are extensive properties, but when you divide them, the ratio remains constant regardless of the system of the size. So which means ratio of two extensive properties is an intensive property. We know that density is the ratio of the mass to volume. Here mass as well as the volume both are the extensive property. So ratio of the two extensive property is an intensive property. So density is the intensive property. So option B is the correct answer. Let's see the next question. The internal energy of an ideal gas is a function of temperature and pressure. Option B, volume and pressure. Option C, entropy and pressure. Option D, temperature only. So we know that internal energy of an ideal gas is a function of only temperature. So option D is the correct answer. Let's see the next question. The Vander-waals equation of state is P plus A by V square into V minus B equal to the RT, where P is pressure, V is specific volume, T is temperature and R is characteristic gas constant. The SI unit of constant A is dash. Option A, joule per kg Kelvin. Option B, meter cube divided by kg. Option C, meter to the power 5 divided by kg second square. Option D, Pascal divided by kc. So let's see the solution. Here given equation is the P plus A by V square into V minus V equal to the RT. So here which is look like the PV equal to the RT. Then so P plus A by V square units and P should be the same and same V minus B and V unit should be the same. So inside the bracket P plus A by V square, both the terms P as well as another term A by V square must be same units of the pressure P. Similarly, inside the bracket of the V minus B, here V as well as the B, both terms must be same units of the specific volume V. So P and A by V square are the same units, that is the units of pressure. Then A by V square equal to the unit of pressure which is equal to the Newton by meter square. So A by V square equal to the Newton per meter square. So A equal to the V square into Newton by meter square. And we know that one the V is the specific volume and the units are the meter cube divided by kg. Then V square units are the meter to the power 6 divided by kg square. Then unit of the A will become the Newton by meter square into V square. So V square units are the meter to the power 6 divided by kg square. Then A will become the units are the here meter square and the 2 will be cancelled here, meter to the power 4. Then units of the A will become the Newton meter to the power 4 divided by kg square. So, and we know that one the Newton equal to the units of the Newton equal to the kg meter per second square. Then you have to substitute in the units of the small a. Then, so Newton we have to substitute kg meter per second square. Then small a equal to the kg meter per second square into meter to the power 4 divided by kg square. So here kg and 1 kg will be get the cancel. Then we will get the units of the A is meter to the power 5 divided by kg second square. Then option C is the correct answer. Let's see the next question. The specific heats of an ideal gas depends on its option A temperature, option B pressure, option C volume, option D molecular weight and structure. We know that specific heat is the amount of heat required to rise the temperature of 1 kg of a substance by 1 degree or maybe the 1 Kelvin. So for small amounts of heat transfer we can be written as dq equal to the mc dt. Here C is the specific heat. And specific heat depends on how energy is stored inside gas molecules. So for example, monoatomic gases, which is the helium and neon, have lower specific heat, and the diatomic gases, oxygen and nitrogen, have higher the specific heat, and moreover polyatomic gases have even higher values. So this happens because of the different molecular structures have different degrees of the freedom. So in this regard, option D is the correct answer. So specific heats of an ideal gas depends on its molecular weight and structure. So let's see the next question. The definition of 1 Kelvin as per the internationally accepted temperature scale is option A 1 by 100th the difference between the normal boiling point and normal freezing point of water. Option B, so 1 by 273.15 normal freezing point of water. Option C, 100 times the difference between the triple point of water and normal freezing point of water. Option D is the, so 1 by 273.16 of the triple point of the water. So we know that one the, so definition of the 1 Kelvin is the 1 by 273.16 of the triple point of the water. So option D is the correct. Let's see the next question. Consider a mixture of two ideal gases X and Y with molar masses of Mx equal to the 10 kg per kilomole and My equal to the 20 kg per kilomole respectively in a container. The total pressure in the container is 100 kilopascal. The total volume of the container is 10 meter cube and the temperature of the contents of the container is 300 Kelvin. If the mass of a gas X in the container is 2 kg, then the mass of the gas Y in the container is dash kg. Assume that universal gas constant is 8314 joule per kilomole Kelvin. So let's see the solution. First you have to write down the given data. So here the mixture of the two ideal gases is given. One is the X and Y. Along with the molar masses of the X and Y gases is given. So let's consider Mx, molar mass of the X ideal gas is the 10 kg per kilomole, and My, which is the molar mass of the Y ideal gas. So My equal to the 20 kg per kilomole. The total pressure in the container is 100 kilopascal. So total pressure, let's consider capital P equal to the 100 kilopascal, which is equal to the 100 into 10 to the power 3 pascal. And also given the total volume of the container is 10 meter cube. So volume capital V equal to the 10 meter cube. and temperature of the contents of the container is 300 Kelvin. So let's consider temperature capital T equal to the 300 Kelvin. If the mass of the gas X in the container is 2 kg, so small mx, mass of the gas X, small mx equal to the 2 kg. So then we have to determine the mass of the gas Y. So that is the my, small my we have to determine. And it is given the universal gas constant R naught equal to the 8314, so joule per kilomole Kelvin. So okay, so first we have to go for the use the ideal gas equation for the mixture. So we know that when the MR equal to the R naught equal to PV by NT. So this we can be written as PV equal to the N R naught T. So where the N equal to the total number of kilomoles, then N total. So total number of kilomoles which is equal to the PV divided by R naught into T. So here we know the total pressure we know, total volume we know, and temperature also we know, R naught value also we know. Substitute. So we will get the N total equal to the, so 100 into, so which 100 into 10 cube, which is the pressure. So Pascal is the Newton per meter square. Okay. So 100 into 10 cube into, so volume is the 10 meter cubed. So into 10 divided by R naught value is the 8314 and temperature is the 300. Then total number of moles will become the 0.4009 kilomoles. So the total number of moles N is the sum of the number of moles of the gases X and Y. So this is we can be written as N total or small n equal to the Nx plus Ny, and we know the relationship between the mass and molar mass. Then we can be express the total number of moles in the terms of the mass and molar mass. So small n equal to the mx small mx, which is the mass of the gas X divided by molar mass of the X gas, that is the capital Mx, plus my small my divided by capital My. So then we know the mass of the X gas is given small mx, we know, and molar mass mx is given the 10 and my you have to determine, and capital My it is given the molar mass 20 kg and the small n value, that is the total number of moles also we know 0.4. Then substitute, equation will become the 0.4 equal to the 2 divided by 10 plus small my divided by 20. So in this regard, so small my equal to the mass of the gas Y is the my equal to the 4. So answer is the 4 kg. So answer is 4 kg. Let's see the next question. The volume and temperature of air in a closed vessel is 2.87 meter cube and 300 Kelvin respectively. The gas pressure indicated by a manometer fitted to the wall of the vessel is 0.5 bar. If the gas constant of air is R equal to the 287 joule per kg Kelvin and the atmospheric pressure is 1 bar, then mass of the air in the vessel is dash. So let's see the solution. So first write down the given data. Volume and temperature of the air is given. Let's consider volume V equal to the 2.87 meter cube and temperature capital T equal to the 300 Kelvin. And gas pressure is indicated by manometer, which is equal to the 0.5 bar. So remember here given the gas pressure. So let's consider gas pressure. P gas equal to the 0.5 bar. We know 1 bar equal to the 10 to the power 5 Newton per meter square. Then P gas equal to the 0.5 into 10 to the power 5 into Newton per meter square. And given the gas constant R equal to the 287 joule per kg Kelvin, and also given the atmospheric pressure, which is the 1 bar. So 1 bar equal to the 1 into 10 to the power of 5 Newton per meter square. So now I have to determine the mass of the air. So we know the relationship, ideal gas relation is the PV equal to the MRT, but this equation is valid for when P is the absolute pressure only. But here in the data it is given the gas pressure and atmospheric pressure, but we have to determine the absolute pressure. We know the relation between the absolute pressure and atmospheric pressure and the gas pressure, which is equal to the absolute pressure equal to the atmospheric pressure plus gas pressure. So then absolute pressure will become the 0.5 plus 1, which is equal to the 1.5 bar, which is the 1.5 into 10 to the power of 5 Newton per, so sorry, it is meter square, not mm square. So Newton per meter square. So we know P value, we know V value, we know, and R value, we know, T value, we know. Substitute all these values in the PV equal to MRT. So then we will get the M equal to the 5 kc. So answer is the 5 kc. Let's see the next question. Temperature of nitrogen in a vessel of volume 2 meter cube is 288 Kelvin. A U2 manometer connected to the vessel shows a reading of 70 centimeter of mercury. The universal gas constant is 8314 joule per kilomole Kelvin. Atmospheric pressure is 1.01325 bar. Acceleration due to gravity is 9.81 meter per second square, and density of mercury is 13600 kg per meter cube. The mass of nitrogen in the vessel is dash. So this is the U2 manometer. In the previous lectures already we discussed. So next I have to write down the given data. The data is given the volume of vessel capital V equal to the 2 meter cube, and temperature of the gas also given, that is the capital T equal to the 288 Kelvin, and so manometer height of the mercury is given. Let's consider Z is the height of the mercury. So manometer reading, let's consider the Z equal to the 70 centimeter, but better have to convert it to the meter, that is the 0.7 meter. And universal gas constant R naught value is given 8314 joule per kilomole Kelvin, and atmospheric pressure is the 1.01325 bar, and 1 bar equal to the 10 to the power 5 Newton per meter square. Then atmospheric pressure equal to the 101.325 Newton per meter square. And also given the G value, gravity 9.81 is given, 9.81 meter per second square, and density of mercury, let's consider rho m equal to the 13600 kg per meter cube. So then you have to determine the mass of the nitrogen in the vessel in the kg. So you have to m value have to determine. So we know the equation PV equal to the MRT. So here P is the absolute pressure, but in the data it is given the atmospheric pressure and the gas pressure. But gas pressure we can be determined by the U2 manometer. And here R is the gas constant, but is given the universal gas constant. We know the relationship is the MR equal to the R naught. Then R equal to the R naught divided by M. For the nitrogen gas, M equal to the 28. Then R value will become the 296.9 joule per kilomole Kelvin. And absolute pressure equal to the atmospheric pressure plus gas pressure. So atmospheric pressure is given the 101.325 Newton per meter square, but gas pressure we don't know. We have to determine the gas pressure. So from the U2 manometer, gas pressure equal to the density of the mercury into acceleration due to gravity into height of the mercury. So that is the rho m into G into Z. So rho m is given, density of the mercury is given. So acceleration due to gravity is given 9.81, and Z, so height of the mercury it is given 0.7 meter. Then substitute, we will get the gas pressure equal to the 93,391.2 Newton per meter square. Then absolute pressure will become the 101,325 plus 93,391.2, which is equal to the 194,716.2 Newton per meter square. So now we know the in the PV equal to MRT equation. So P value we know, that is the 194,716.2, and R value we know, R naught divided by M, that is the 296.9, and T is, we know that one, the 288. Then substitute. So we will get the M equal to the 4.55 kc. So answer is the 4.55 kc. Let's see the next question. A certain amount of an ideal gas is initially at a pressure P1 and temperature T1. First, it undergoes a constant pressure process 1 to 2 such that T2 equal to 3T1 divided by 4. Then it undergoes a constant volume process 2 to 3 such that T3 equal to T1 by 2. The ratio of the final volume to the initial volume of the ideal gas is dash. So let's see the solution. So here given the ideal gas. So we know the ideal gas relation equal to the PV equal to the MRT. And initially gas is at pressure P1 and temperature T1. First it undergoes a constant pressure process 1 to 2. So process 1 to 2 is the constant pressure process. So P1 equal to the P2. And we know the relation is the PV is directly proportional to the T. So P equal to the constant, which means, so V is directly proportional to the T. So from this one we can be written as V1 by V2 equal to the T1 by T2. So from this one we can be written as V2 by V1 equal to the T2 by T1. So moreover it is given in the data. T2 value is the 3T1 divided by 4. So then we have to substitute here. We will get the V2 by V1 equal to the T2 value is the 3T1 divided by 4. Then T1 get cancelled. Then V2 by V1 equal to the 3 by 4. And V2 equal to the 3 by 4 into V1. And next one is the, then it undergoes a constant volume process 2 to 3. So process 2 to 3 is the constant volume process, which means V2 equal to the V3. Then we know the relation. So V2 value we know, that is the 3 by 4 V1. Obviously V3 value also 3 by 4 V1. So then we have to determine the ratio of final volume to the initial volume. So final volume is the V3, initial volume is the V1. Then we have to determine the V3 divided by V1. So from this equation we can be written as V3 by V1 equal to the 3 by 4. So answer is the 3 by 4. So let's see the next question. A football was inflated to a gauge pressure of 1 bar when the ambient temperature was 15 degrees Celsius. When the game started next day, the air temperature at the stadium was 5 degrees Celsius. Assume that the volume of the football remains constant at 2500 centimeter cube. The amount of heat loss by the air in the football and the gauge pressure of air in the football or the stadium respectively equal. Option A 30.6 joule, 1.94 bar. Option B 21.8 joule, 0.93 bar. Option C 61.1 joule, 1.94 bar. Option D 43.7 joule, 0.93 bar. So, okay, so let's see the solution. So here given the gauge pressure. So initial gauge pressure is the 1 bar. Let's consider Pg1. Initial gauge pressure is the 1 bar and ambient temperature is given the 15 degrees Celsius, which means initial temperature T1. Let's consider T1 equal to the 15 degrees Celsius, which is equal to the 288 Kelvin. And moreover, we know that when the atmospheric pressure is the 1.01 bar. So I have to remember this atmospheric pressure 1.013 bar. And we know the relationship between the gauge pressure and the absolute pressure. So initial absolute pressure equal to the P1. Let's consider initial absolute pressure P1 equal to the initial gauge pressure, that is the Pg1 plus atmospheric pressure that is the 101, 1.013 bar. Then P1 value equal to the 1 plus 1.013, which is equal to the 2.013 bar. So initial absolute pressure value, we got it. And the next to given the final temperature, air temperature at the stadium was 5 degrees. So final temperature, let's consider T2 equal to the 5 degrees Celsius, which is equal to the 273 plus 5, 278 Kelvin. And assume that the volume of the football remains constant. So volume is the constant, and given the volume V equal to the 2500 centimeter cube, which is equal to the 2500 into 10 to the power of minus 2 whole cube, which is equal to the 10 to the power minus 6 meter cube. So then you have to determine the amount of heat loss by the air in the football and the gauge pressure of the air in the football at the stadium. So I have to Q and PZ2 have to determine. So this is the given data. So first you have to determine the final gauge pressure of the air in the football, that is the PG2 have to determine. So we know the gauge pressure and the absolute pressure. So have to determine the final gauge pressure. So final absolute pressure P2 equal to the PG2 plus P atmospheric. So we know the atmospheric pressure we know, but we don't know P2 value, we don't know to determination of the gauge pressure. So from this equation we can be written as Pg2 final gauge pressure equal to the P2 minus P atmospheric. So first I have to determine the P2 value, have to determine. So here process is the constant volume process. In the constant volume process, so PV is directly proportional to T, then volume is constant, mean P is directly proportional to T, then P1 by T1 equal to the P2 by T2. So here P1 value we know, and T1 value we know, T2 value we know. So from this one, P2 equal to the P1 into T2 by T1. Substitute all the values, then P2 value is the 1.93 bar. So we know the final absolute pressure P2 value we know, and atmospheric pressure we know. Then gauge pressure will become the 1.93 minus 1.01013, which is equal to the 0.917 bar. So okay, so we determine the final gauge pressure. So then I have to determine the heat loss. Q have to determine. We know Q equal to the mCV dt. So here m value we don't know. So in this regard I have to use the PV equal to the MRT equation. So P, so initial temperature, and we have to use the initial absolute pressure we have to use. For this one, initial absolute pressure equal to the 2.013 bar, which is equal to the 10 to the power of 5 Newton per meter square, into volume is the 2500 into 10 to the power minus 6 equal to the mr and T capital T. So initial temperature is the 288, and R value we know that one, the for the air we have to remember this one, R equal to the 0.287 kilojoule per kg Kelvin, and R equal to the 287 joule per kg Kelvin, and substitute R value. So from this equation m equal to the, so mass equal to the 0.006083. So we know mass value we know. So then have to go for the heat loss equation. M value we know, and dt. So final temperature minus initial temperature we know, and CV value. So should have to remember CV value for the air, which is equal to the 718 joule per kg Kelvin. So substitute all the values. Then Q equal to the mass 0.006083 into CV 718 dt temperature difference. So which is the 278. So final temperature and initial temperature 288. So 278 minus 288, we will get the minus here. So minus represent the heat loss. So Q equal to the minus 43.7 joules, which is the Q heat loss equal to the 43.7 joules. So here we determine the heat loss Q equal to the 43.7 joules, and the gauge pressure, it is the nearly, let's consider, maybe small mistakes will become. So it is the 0.93 bar. So option D is the correct answer. So let's see the next question. Match items from groups 1, 2, 3, 4, 5. Group 1 is indicating the E heat, F work. Group 2 is indicating the when added to the system is G is the positive, H is the negative. Group 3 is indicating the differentials. So I is the exact differentials, J is the inexact differentials. And group 4 is the function. K is the path function and L is the point function. And group 5 is the phenomena, M is the transient phenomena and N is the boundary phenomena. So then I have to match the following. So let's see first here. So in the options I have to observe, one is given the heat point of view, another one is given the work point of view. Okay, let's see match here. So when heat is added to the system, it is the positive. So E and G. And so these are all the not exact differentials. So it is the J. So EJ. Heat as well as the work, both are the inexact differentials. So I am forming the from the heat point of view. And next one is the both are the path functions. So it is the K. And it is the heat and work, both are the boundary phenomena. So N. Similarly, you have to match the items from the work point of view. So work is the F, and so when it is added to the system, so it is the negative, so H, so FH, and it is also inexact differential, so it is the J, and it is also work also path function, and it is also boundary phenomena. So EGJKN, so EGJKN, so here it is there, and FHJKN, so FHJKN also there. So these both are given for the option D. So option D is the correct answer. So next question is the an isolated thermodynamic system executes a process. Choose the correct statements from the following. So no heat is transferred. We know that when in the isolated system there is a no heat transfer, no work done, and no mass flow across the boundary of the system. So these three are the correct. And no chemical reaction takes place within the system. No, it is the wrong. So except the option D, remaining three are the correct. So these are the GATE previous questions for the basics of thermodynamics and the Zeroth law. And thank you.